Hey, it turns out that 0 over 0 and infinity over infinity are not the only indeterminate forms. We finish our study of L'Hopital's rule by considering 4 others. And let's start with this example here. As x approaches 0 from the right, the natural log of x is approaching negative infinity. And so here we have something of the indeterminate form 0 times infinity. 0 times anything should be 0, but multiply something by infinity, of course it should get big, and so who knows what happens. And the trick for a problem like this is to do some algebra to rewrite the expression either in the form infinity over infinity or 0 over 0. For example here, dividing by 1 over x, same thing as multiplying by x over 1, or just x. And so these are the same expression algebraically, but as x approaches 0 from the right, natural log of x goes to negative infinity, and 1 over x goes to positive infinity, and so this is of the form infinity over infinity. And that means we can apply L'Hopital's rule. We get that this limit is equal to the limit as x approaches 0 from the right of the derivative of the numerator, and the derivative of the natural log of x is 1 over x, divided by the derivative of the denominator, and the derivative of 1 over x is negative 1 over x squared. And all that's left is to do a little simplifying. 1 over x divided by negative 1 over x squared simplifies eventually just to negative x, and as x approaches 0, negative x approaches 0. And so the limit here is 0. One thing you might be wondering is, could you have done this differently? Algebraically, x times the natural log of x could also be written as x divided by 1 over the natural log of x. And since the natural log of x goes to negative infinity as x goes to 0 from the right, 1 over the natural log of x is going to 0. And so this is of the form 0 over 0. And so we can again apply L'Hopital's rule, in this case looking at the limit as x approaches 0 from the right of the derivative of the numerator over the derivative of the denominator. And in order to take the derivative of the denominator without having to use the quotient rule, it might be helpful to rewrite 1 over the natural log of x as natural log of x to the negative 1. And then by L'Hopital's rule, we get the limit as x approaches 0 from the right of 1 in the numerator, and in the denominator, by the chain rule, we get negative natural log of x to the negative 2 times the derivative of natural log of x, which is 1 over x. And after you do some simplifying, you come up with the limit as x approaches 0 from the right of negative x times the natural log of x all squared. And look at what's happened here. We started with a limit that we were trying to find that was in the form 0 times infinity and wouldn't allow us to apply L'Hopital's rule directly. And we did a bunch of algebra, and we came up with a more complicated limit that still does not allow us to apply L'Hopital's rule directly. Here we have x times natural log of x squared, still in the form 0 times infinity, but even more complicated than the original limit. And that's our indication that this was a mistake. I mean, it's correct algebraically, but in terms of a strategy for trying to find this limit, it doesn't get us there. It makes things harder. Whereas this, which we did over here first, also correct algebraically, and in terms of a strategy, it works. It gets us some limit that we can actually compute after we apply L'Hopital's rule. And the moral of the story, for these limits in the form 0 times infinity, you have to rewrite them algebraically in the form infinity over infinity or 0 over 0. Well, if you try it one way and it gets worse, stop, go back, and try it the other way, and that will probably make it better. Here are the other indeterminate forms. Something of the form 0 to the 0, infinity to the 0, or 1 to the infinity. 0 to the anything should be 0, and yet anything to the 0 should be 1. Infinity to anything should certainly be a large number, infinity perhaps, but anything to the 0 should be 1, and 1 to any power should be 1, but infinity is a very big power. And so all of these are indeterminate forms, and it turns out with some trickery, we can use L'Hopital's rule to solve limits like this. And the trickery, luckily, is the same for limits of each of these 3 types. Let's start with this example. The limit as x approaches infinity of 1 plus 1 over x all to the x. As x approaches infinity, 1 over x is approaching 0, and so this is of the form 1 to the infinity. Here's how these problems work. You set some variable that we usually call y equal to the limit that you're trying to compute, then take the natural log of both sides and use the properties of logarithms to make some progress. And that's what I've started to do here. I let y equal the limit that I'm trying to compute, and then I take the natural log of both sides so that the natural log of y is the natural log of the limit that I'm trying to compute. The next step is really the key step, and the argument is, since the natural log is a continuous function, the natural log of some limit is actually equal to the limit of the natural log of the function. In other words, you can interchange the log and the limit in this situation. And that's what I've done here. I've replaced the natural log of the limit as x approaches infinity of 1 plus 1 over x to the x with the limit as x approaches infinity of the natural log of 1 plus 1 over x to the x. And the beauty of that maneuver is that it lets you use the properties of logarithms. The natural log of something to the x is x times the natural log of that something. You can bring the exponent in front of the logarithm. And that gives us that the natural log of y is the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. And this is of the form 0 times infinity, or infinity times 0 technically, because as x approaches infinity, well, the x is of course approaching infinity, but the natural log of 1 plus 1 over x, well, 1 over x is approaching 0, and the natural log of 1 is 0. And we know how to deal with limits of the form 0 times infinity. We rewrite them algebraically as something of the form 0 over 0 or infinity over infinity. And we'll treat this one very similarly to the way we treated the last problem. Multiplying by x, same thing as dividing by 1 over x, and rewriting it that way, this is now of the form 0 over 0, which lets us apply L'Hopital's rule. And you have to be a little careful taking the derivative. In the numerator, you need the chain rule. You treat the 1 plus 1 over x as if it were a variable, and so that gives you 1 over 1 plus 1 over x. And then you multiply by the derivative of that function you just treated like a variable, and the derivative of 1 plus 1 over x is negative 1 over x squared. Similarly, in the denominator, the derivative of 1 over x, negative 1 over x squared. Looks horrible at the start, but really not so bad at all. The numerator and denominator both have a factor of negative 1 over x squared, and those cancel. And that leaves us with the natural log of y equal to the limit as x approaches infinity of 1 over 1 plus 1 over x. And as x approaches infinity, 1 over x approaches 0. And so that limit is actually very easy to take, and we get the natural log of y is equal to 1. Now we have to remember what we were trying to figure out. Y is the original limit that we were trying to compute. So we need to know not what the natural log of y is equal to, but what y is equal to. And since the natural log of y is 1, e to the natural log of y is equal to e to the 1. And the beauty there is that e to the natural log of y is just y. And so we find that y is equal to e. And just to be very clear about it, what we've just shown is that the limit as x approaches infinity of 1 plus 1 over x to the x is the number e. In other words, these values, 1 plus 1 over x to the x, converge to this number between 2 and 3 that we call e as x goes to infinity. Quite amazing. Okay, you try this one, do it exactly the same way. The limit as x approaches 0 from the right of x to the x. Set y equal to it, take natural log of both sides, interchange the log and the limit, go from there. Before you start, just a note, why are we taking x approaching 0 only from the right? Well, consider what happens at some of the negative values. For example, what if x was negative a half? Then we'd have negative a half to the negative a half power, which is 1 over the square root of negative a half. And there is no real number that's a square root of negative a half. So to the left of 0, this function is not defined at every real number, only at some of them. At some of them it is, at some of them it isn't. And so we'll stay safe and only look at the limit as x approaches 0 from the right. Okay. Take a few minutes, give this a try, pause the video. When you're ready, start it up and we'll do it together. First step, set y equal to the limit that we're trying to compute. Second step, take the natural log of both sides. And then what's really the key maneuver, interchange the logarithm and the limit. Use the idea that the logarithm is continuous. That lets us exchange the logarithm and the limit. And now we can use properties of logarithms. The natural log of x to the x is x times the natural log of x. This is of the form 0 times infinity, and so we can do some algebra to put it into some form that we can actually apply L'Hopital's rule directly. But if you go back to the beginning of the video, we already did this problem. And so work it out slowly and carefully for yourself if you like, but we've already done it and we found that this limit is equal to 0. And so we have the natural log of y is equal to 0. We'd like to know what y is equal to. And so we raise e to both sides, and that tells us that y is equal to 1. In other words, the answer to the problem, the limit as x approaches 0 from the right of x to the x is equal to 1. Not at all obvious, and yet we've shown that it's true. Okay, now you know everything that you need to know about L'Hopital's rule. You should be able to do every problem on the homework. Have some fun with it. See you soon.